Hello, Math 3 to 11 students. Let's begin Lesson 7, Congruence Theory, Part 2. Lesson 6 covered up to Section 3. Now let's begin Lesson 7 with Section 4, the Chinese remainder theorem. We begin with a system of linear congruences, and this system is fundamentally different from the system that we considered in Section 3. In Section 3, we studied a system of linear congruences with the same modulus, mod 13 for all, mod 15 for everything, mod 9 for everything, things like that. But this time, we have mod M1, mod M2, mod M3, and so on. They're all different. Not only that, they have to be all pairwise relatively prime. We need stronger condition. So in a sense, this kind of system sits on the opposite end of the extreme. M1, M2, M3, and so on, they are all completely different in a sense that they consist of distinct prime factors. None of them shares any prime factor. In contrast, in Section 3, we deal with the linear congruences with same modulus, same M all over. So this is kind of polar opposite of the previous case. And then one more. Capital M is a product of them all, and because they are all pairwise relative prime and thus they do not share any prime factor, this capital M is actually LCM. The product of them all is actually the least common multiple. The conclusion is that the system has a unique solution modulo capital M. Okay, how to prove that? And it's done in multiple steps, but please remember all those steps, at least up to Section 3, because you're going to need all those in order to actually do your own computation. You're going to see those in example problems. Okay, let's begin. First, preparation. We define capital M1, capital M2, and so on by multiplying all the moduli except for the kth one. So multiply everything else, or equivalent speaking, multiply everything and then divide by the kth. So we have this kind of division. So mk cancel out. What's left is the product of everything else. So that's capital MK. And please note that this capital MK and small mk have to be relatively prime. You see, all those small m1, m2, m3, all those are pairwise relative primes. So none of them shares any of those prime factors. So all the prime factors of mk, none of those is shared by any of those other mi's, and that's how you get capital MK. So they do not share any prime factor. So they are relatively prime. And consequently, we can consider the multiplicative inverse of capital MK modulo small mk. Remember the modular inverse condition, this one here. Capital MK goes in place of A, and small mk is this M. So thanks to this pairwise relatively prime condition, capital MK is relatively prime to small mk, so it has multiplicative inverse, modulo small mk. We're going to call it mu k. So capital MK times mu k is 1. Okay, we are ready. The solution looks like this. A1 capital M1 mu 1, A2 capital M2 mu 2, and so on. Multiply all these, A and capital M and mu, for the first, second, third, and then add them all up. And that is the solution. Let's see. It's not too difficult to see that this is actually a solution. this M1, oh, I was a bit premature closing everything. This M1 is product of all the mi except for the first. And capital M2 that comes next is product of all the mi's except for the second and so on. And we are particularly interested in the kth one. For that kth, this mk is included in this product. And the second, third, fourth. And then other than kth, they're all that mk is all included here. So the result, M1 includes small mk, M2 equals capital M2 includes small mk and so on. So all those capital M's are zeros. And then capital Mk times mu k, that's only non-zero modulo mk. But then again, that's multiplicative inverse, so this is 1. So all 0 except this one, which is 1. So what do you get in the end? X is congruent to ak modulo small mk. So anything other than capital Mk, Mk is included in this multiplication. So that's congruent to 0 modulo small mk. So what did you just prove? This is indeed a solution. Now how about the unique solution? What if there are two solutions, x1 and x2? Well, x1 and x2, both of them satisfy the system. So for each k, x1 is congruent to ak modulo mk, and same goes to x2. Therefore, if I subtract one from the other, you're going to get x1 minus x2 is congruent to ak minus ak, which is 0 modulo mk. So what conclusion can I draw? mk divides x1 minus x2, and that's true for all k, first, second, third, and so on. Consequently, this x1 minus x2 is divisible by the LCM. This is common multiple, so it's divisible by the least common multiple. What's the LCM? These are all pairwise mutually prime, pairwise relatively prime. So LCM is just a product. So capital M happens to be LCM, so that divides this x1 minus x2. In other words, x1 and x2 are congruent modulo capital M. That proves the uniqueness. I don't think you have to reproduce the uniqueness out of nowhere, but as for up to step 3, please remember, the preparation is to get capital MKs and then get mu k, multiplicative inverse, and then once you got them all, then multiply each and add them all up to get the solution. I hope I made sense. Well, one way to solidify that understanding is to go through an example problem. Let's go ahead and do that. Here's an example problem, and this one is the first known example of a problem associated to the Chinese remainder theorem, published sometime in 1st century AD. But whether this was discovered by Sun Tzu or it was known earlier, it's quite unclear, as a matter of fact. And the first known proof was by Qijun Qiao in 13th century. But whether this was actually done for the first time by this person or not, was it older, is a little bit unclear. You have to understand that because these are all old results. And all the publications, discovery and crediting all those, none of those were settled at that time. And especially in China, whenever something new is discovered, a lot of people, a lot of political factions kept those secret. and then only occasionally they were published as books to disseminate this to others. And by that time, it already became common knowledge. That's why they were being published. So it's really unclear whether these are discovered by these people. First example by Sun Tzu, 1st century, or first proof by Pigeon Chao and 13th century. But those are oldest known results. Okay, so much for historical background. Let's go ahead and solve this problem. And the solution is pretty much parallel to what we did earlier. Preparation is finding capital M case. Capital M1, capital M2, capital M3 by multiplying all those moduli, 3, 5, and 7, dividing by 3, 5, and 7 respectively, or multiplying the other moduli. Either way, you get 35, 21, and 15 respectively. And then we want to find that mu1, mu2, and mu3, right? Multiplicative inverses of those. Here's mu1. Capital M1 is 35, so 35 is congruent to 2 modulo 3. And 2 inverse is 2. 2 times 2 is 4. That's congruent to 1 modulo 3. We do the same thing for mod 5. M2 is 21, and that's congruent to 1 mod 5s. So that inverse is easy. And this inverse is also easy. 15 inverse is 15 is 1, so 1 inverse is 1. Anyway, we have all those. And then now that we have A1, A2, A3 here in the original problem, and capital M1, capital M2, capital M3 in step 1, and then mu1, mu2, mu3 in step 2, I can multiply all those and add them up like this to get the answer. And from this point on, just a routine computation. In the end, we get 128. That's congruent to 23 modulo 105. So, step 1, capital M1, capital M2, capital M3. Step 2, their multiplicative inverses. Step 3, the final answer. Do we have enough time for another example problem? Let's try. Here's a variation, modulo 5, 6, and 7, and please note that they are all pairwise relative to the prime. And step 1 is a preparation. We want capital M1, capital M2, capital M3. And then let's find out their inverses, mu1, mu2, and mu3. 42 is congruent to 2, so 2 inverse, mod 5. 35 is congruent to 5, and that inverse. 30 is congruent to 2, mod 7, and that inverse. You end up with 3, 5, and 4 respectively. Those are mu1, mu2, and mu3. So we can put everything into this form. A1, capital M1, mu1. A2, capital M2, mu2, and so on. A1, A2, A3 are here. 1, 2, and 3 respectively. Capital M1, capital M2, capital M3 are here. And then mu1, mu2, mu3 are in step 2. So put them all together and run your calculator, basically. Well, okay, let's pretend we are back in 1st century, so no calculator. In the end, you get 206 modulo 210.